So I've given you one definition for doing a proof by induction. And notice here that it's for statements that look like for all integers, prove that some statement is true. Well, what happens if you ran into a case where you're being asked to prove this kind of statement, but not over the natural numbers, but over a different set? So it turns out that proofs by induction can still work even if you're not just talking about the natural numbers. In other words, we can substitute out this set right here. That set, though, has to have a special property. So I'm going to define that special property right now. So a set, so a collection of objects, a collection of numbers, a collection of anything, is called countably infinite, which I will be abbreviating CI, countably infinite if the following is true. So a set is countably infinite if we can uniquely label everything in the set by 1, 2, 3, 4, etc. by all the natural numbers. So, for example, this set right here, 5, 6, 7, 8, 9, 10, etc. In other words, all natural numbers bigger than 5. This is countably infinite. Why is this countably infinite? Well, because it's pretty easy to be able to label these things, right? So we could label this as, that gets label 1. The next one gets label 2, etc., etc., etc. So it's pretty easy to see that we can uniquely label every single one of its elements by 1, 2, 3, 4, etc., etc. As another example, the set of all real numbers, so all the fractions, irrational, pi, everything, plus and minus, natural numbers, etc., that set right there is not countably infinite. And if you want to know why that's the case, you can ask me about that sometime. The set of rational numbers, so I don't think I've introduced this symbol before, but this thing is equal to all numbers that can be expressed as fractions. So if you take any old integer divided by another integer right there, that's going to be a rational number. It is countably infinite. And you can ask me about that sometime because it's pretty interesting to show how that thing is countably infinite. So why am I talking about countably infinite? Because it turns out that induction is going to work on any countably infinite set. So if you run into a case where you're asked to prove something and it's not just the natural numbers, as long as it's a set that has this special property, then we are going to be able to use a proof by induction. And so that's what we're going to discuss next, is how to do a proof by induction when we're not talking about the natural numbers, but we're talking about one of these special sets right here.